first one is going to be looking at an analysis of looking at the size limit in the commercial halibut fishery. There's been a lot of discussion over the last several years about the potential for changing the size limit. Will that allow us to take any advantage of small fish that might be present in the population? And the second set of presentations will be on harvest policy considerations and an update on where we're sitting on the management strategy evaluation. So I'll ask Juan Valero to do those presentations, please.
Hello. So this presentation will focus on analysis on potential effects of potential changes to the current minimum size limit in the commercial fishery for Pacific halibut. And just as a note, if you're looking for material relevant to this talk, is in page 195 of this year's ORARA or page 22 of the blue book most of you have in your hand. So as a brief history of the minimum size limit, all of you know the current minimum size limit for the commercial fishery is, it's 32 inches, or it's equivalent of 81.3 centimeters. But that has changed through the history of this fishery. From at the beginning of the fishery in 1988, the commercial fishery, to 1943, effectively there was no size limit. Starting in 1944 to 1973, sorry, the minimum size limit changed to 26 inches or 66 centimeters, and the current minimum size limit of 32 inches or 81.3 centimeters has been in place since 1974. As you just heard, we've had requests to staff to evaluate the potential effects of lowering the size limit. So among the rationale for those requests of analysis for lower the size limit can be counted the fact that for Pacific halibut, females tend to grow at a faster rate than males. What we have here is halibut size by age. As you see, the females are growing faster, and when you have a minimum size limit, which is this line here, that effectively means that a female for the same age will have a higher probability of being caught if selectivity is based by the size of the fish. And I will define very briefly here selectivity, and you have a definition of that in one of those pages that were provided to you with definitions. Basically, selectivity is the relative probability of a fish of being retained or landed by any of the fisheries based on its properties such as size, if you assume that selectivity is at size, age, or other characteristics of the fish. That's what selectivity is. As I was saying, the fact that females grow faster than males, effectively what it means is that when you have a fishery on it, you are removing them at a quicker pace than males, because males grow at a slower rate. So effectively what you expect to see in that case, if we have here the proportion female on the population between 0, that is no females, and 1 of females, is that for the younger ages, the proportion is expected to be about half and half. And then since you're fishing mostly on females, that proportion begins to decline with age until basically what you have left for older fish are mostly males. And that gets translated, if you will, into what we see, or we estimate to see on the commercial catch, the proportion female on the commercial catch. That is, for younger fish, say ages 6 to ages 10 or 12, most of them are actually females. There are very, very few males that are caught of those ages. This gets compounded by ongoing declines in size at age. That is, if we had to measure the changes in size for each of the ages, or the growth, if you will, of an average female, post-wild female, if you will, in 2002, we would have gotten basically this curve here. By 2011, it had come down, and the same thing for males. Another aspect of the rationale has been the estimates of very large and increasing total biomass that is composed of halibut ages 8 and plus. This is estimated by recent stock assessments, and effectively is estimating that there's lots of fish out there that are small or young. This contrasts with recent declines in trends of eBio. These are both estimates from recent cost-wide assessments at the cost-wide level. And this contrasts also with the ongoing decline on the data itself, which is the survey data, which has been a continuous decline since the inception of the survey. So this difference between a declining estimate of eBio, declining survey, but an increasing estimated trends of TBio have prompted also requests of, or perhaps there's a way to safely tap into those total biomass. So how can we actually go about estimating the potential effects of changing the minimum size limit? Well, there are many of them, and they all are going to be mainly based on what we assume is going to happen with selectivity. That is, every time we're going to do something with the minimum size limit, then the fishery is going to be potentially or most likely prosecuted in a different way. And if we're talking about decreasing the size limit, it will mean effectively that smaller fish are going to start to be retained. So among the approaches we follow, the first one was the one that makes the least assumptions. It's just to look at effective female selectivity and maturity at age, and this is based on life history theory. The second one is straightforward single area yield per recruit and biomass per recruit. That involves making more assumptions and modeling. Then a migratory yield per recruit and biomass per recruit analysis. This is similar to the one area, but now has multiple areas and migrates fish. So again, makes further assumptions. So in terms of that important process, selectivity, and what assumptions can we make when we're changing or evaluating changing the size limit, what we have here is that selectivity between 0 to 1, Halibut size, here is 81.3, so that's the current minimum size limit. And what we have here in the open circles is the currently estimated cost-wide commercial selectivity. In black is the currently estimated cost-wide survey selectivity. So those are the estimates that we have for that come up basically from the data and for the modeling of the assessment. So this one that we have here on the left is assuming that a change in the minimum size limit, effectively by lowering pretty much to the extreme with the current type of gear that we use, it will result in a large change towards smaller sizes in the population. So that's basically the assumption that we make for this extreme case, if you will, for these three approaches. The other assumption that would entail changes in minimum size limit is that the fishery, instead of actually have this type of current selectivity, will shift to the selectivity that we currently estimate for the survey. That is, assuming if there's no size limit or the size limit is smaller, the commercial fishery may fish to something similar to the survey. The other approach is to actually estimate or to come up with gradual changes in selectivity as a function of gradual changes in minimum size limit. And again, the further down we go, the more assumptions we have to make regarding how selectivity and other processes are going to change. Here we can try to model those, for example, by assuming that those gradual changes in minimum size limit will result in an increase in the selectivity of fish below 90 centimeters. This would be, for example, if there's less shaking in the commercial fishery because you can now keep smaller fish, but larger fish are going to remain selected as they are now. That's what we call pattern A. Pattern B is actually shifting gradually the whole selectivity curve to the left. That is, assuming the shape doesn't change, the only thing that it changed is the proportion of all fishes relative to their size that are going to be selected to the gear. And this will be, for example, if changes in size limit will be accompanied by changes in hook size or hook spacing to target the smaller fish. Into the first approach, again, those are the selectivities that we've looked at. Just look at the current situation, or if a change in size limit will entail a change in selectivity to that of the survey or that commercial shift to the left. what we compute after this selectivity at length is the effective selectivity at age by using average coast-wide size at age. And this is only for females. The focus of this part is only on females. So what we see here is like, well, this is the effective selectivity at age in the current situation. If we actually fish, the commercial fishery were to fish like the survey, that one with solid dots there. If you were to fish like a shifted commercial, it's the one on dotted lines. So the point here is to compare, if you will, how quickly a female starts to be selected to the gear with respect to the available estimates we have for female maturity. So every time that a curve is going to be to the left, it's meaning effectively that we are catching immature females at a faster pace than they are maturing. So effectively we're catching more immature females in this situation than if we were to be in the other case. So this is only for the coast-wide situation. As we know, we have several areas and different areas. In this case, I'm just pulling all of area 4 into one big blob to make the presentation shorter. And each of these areas have differences in size at age. That means that these selectivities at age are going to be different for each area. And that's what we see in these plots out here. So each color that you see here, the green, the orange, the blue, correspond to this map for those not familiar with the geographic scope of our fishery. So in the current situation, the estimates of commercial selectivity at age effectively show that for area 2 in particular, we have capture, in the current situation, we have some capture of, or we're expected to have some capture of immature females, particularly above age 11. And then other areas such as, for example, area 3 and most of the part for area 4, we are starting to catch those fish in the commercial fishery after they mature. If we were to fish like the survey, effectively what this does is to shift those selectivities to the left, so there's an increase in the capture of immature females. And if we were to, basically for all of the areas, and if we were to, if the change in size limit were to result in a shift to the left in selectivity at age, effectively that will mean that we will be catching for most areas females at about 3 years before they mature for all of the areas. Again, this is based on these calculations of selectivity at length and selectivity at age and doing it by each of the areas. The other way to look at this, that actually makes less assumptions, is instead of modifying those estimates of selectivity at length and at age, just look at the raw landings. And this is a cumulative plot, so effectively what it does is calculates how quickly you reach the age by which you catch all of the fish of that age. So effectively this is an analogous, if you will, of selectivity. So in the case of the commercial fishery, in this case it's year 2009, again, maturity, female maturity is in black. So we see that for areas 2A and 2B, we are catching a larger fraction of immature females than in the other areas, for example, most of area 4 and area 3A. And you saw some of this in some of the plots that Stephen Hare has presented in past stock assessment presentations, and you see an example in his presentation today as well. So if the fishery, commercial fishery were to fish like the survey, this is what it shows here, again, female maturity in black, that will entail now that a larger number of areas will be expecting to catch a larger fraction of immature females. This is basically this part of the curve here. And will be protected, if you will, first to be mature rather than being caught, only for area, in this case, 3A and 4B. Another way to look at this, and this again making the least possible assumptions regarding changes in what changes in minimum size limit may do in the future if we were to follow that route. Rather than doing it through modeling, we can just look at the past. We've been there before. So we had, as I mentioned before, a period of the early inception of the minimum size limit. So it will be years before that plot here. And as we see, the proportion of immature females. In this case, we cannot tell actually if they're females or males, so these are both sexes combined, but since males still were expected to have been growing at a slower rate than females, probably it's expected that most of these proportions were females. Effectively, the maturity curve, female maturity curve, it lies to the right of the commercial landings at the beginning of the current size limit. In a period with a size limit of 66 centimeters, again, most of the landings were outpacing female maturity. And in the period of no minimum size limit, as we can see here, it was the most extreme of all cases. That was about immature females were captured at a rate or retained a faster rate by about 4 years before they mature. An important caveat needs to be made here is that the estimates of maturity, the female maturity we have, are the ones that we use for the assessment, and then the ones for the recent decades. We do not have similar estimates of female maturity for, say, the earliest years. Second part of the analysis is the yield per recruit and spawning biomass per recruit. I will not go much into details, but just suffice to say that going from the coast-wide selectivity at length, then we need to compute coast-wide selectivity at age for both sexes, blue and pink, and also for the different selectivities. So we'll jump straight into the results for timing. This is to illustrate that if we were to continue to use the current harvest rate, which is here 0.215, this is basically the status quo of where we are now, and these are under the two different assumed selectivities. So if we were to stick with the same harvest rate and shift the selectivity to capture smaller fish, and we can see here what the impact will be. So if we were to fish, if the commercial fishery were to fish like the survey, we see that it will be actually a decrease on the yield per recruit. That is how much poundage we're getting for each fish or each halibut that recruit to the fishery. So it's a slight decrease of about 3%. And actually, if we were to fish drastically to the left of the commercial fishery at present, that will have an increase in yield per recruit of about 14%. But these, as most things in life, come with consequences, and the potential pros here come with a drastic reduction in the level of protection to the stock. So a way to measure the protection to the stock is to calculate what is called spawning biomass per recruit. That is how much a recruit will contribute to spawning biomass through its lifetime. And as we see, the current situation allows us to be at a place that we protect 37% of that biomass that will be expected if there were no fishery in a virgin stage or state or unfished state. So that's the status quo. So if we try to protect the spawning biomass by the same amount we are doing now with the current size limit and harvest rate, is the analysis that was going to be next. But if we just stick with this harvest current target harvest rate, effectively that would mean that rather than being at 37% of unfished, we were expected to be at 31 or 17, which is protecting, in this case, the spawning biomass by 47% of what we're protecting now. And that's effectively what I said here, so I will not go into that. If we constrain the analysis to actually have the same level of protection, so now we ensure that whatever we do, we protect the spawning biomass at the same level. Effectively, what this shows is that we will have to have a precise control of lower target harvest rates, because we're fishing at smaller fish that will have produced more spawning biomass had we left them in the water, so we actually need to exploit them at a lower rate to be able to result in the same level of protection. And even if we do so, the yield per recruit is expected to decline by about 10%. So there's not much to gain by even protecting the same level of biomass per recruit. That's basically what I just said here. The other part of the analysis, this is again on the yield per recruit part, is to look at what the proportion female will be expected to change, or will it change or not by much if we actually change the minimum size limit and therefore the selectivity of the commercial fishery. So as we said, as I mentioned before, these white dots are the current case by which in the population the proportion female decreases rapidly with age, and that's the harvest rate that we are using on the stock, or the target harvest rate that we have for the stock. So if we were to fish like the survey, we see that the proportion of females still declines rapidly with that survey selectivity, and although you have a large change, a relative change, say for age 25, it goes somewhere like around 12% females left in the water by age 25 to about 21%. So it looks like a big change, but still the proportion female in the population is relatively small. And that will entail, again, a smaller, lower harvest rate. So this case will be the case that will be expected if there was no fishery. That is 50% females and males, assuming they have the same natural mortality, so on and so forth. So the only case where we get an increase in the proportion of female by several ages, or by older ages, is if we were to use a target harvest rate of about half of where we are now, and in that case the commercial shift, or the commercial selectivity shifted drastically to the left. This will still entail the capture of immature females, as we saw in the previous analysis, so a precise control of that lower harvest rate will be paramount in that case. Still, the proportion female in the catch will be the highest under these two scenarios, and again, in a similar case, the proportion of female in the catch will decrease, but only if we fish precisely at a very low harvest rate and with the risks that entail. Third part of the analysis is the migratory yield per recruit and biomass per recruit. It's the same approach as before, but now we incorporate these 6 regulatory areas, again, pooling area 4 for expediency. For those not familiar with, or those that are familiar, but just a reminder, the predominantly direction of migration is as shown here, predominantly going from the north to the south. And if you want to read more about it, Ray Webster has a number of reports in past years, and we have a report in this year's RARA. And effectively, migration was modeled in this case following 2 scenarios. One, assuming that halibut of all sizes move at the same rate. That is what I call the one migration matrix assumption. The other one is taking into account the evidence showing that smaller fish move at different rates, typically faster than larger fish. In this case, this is what it shows here. This is yield per recruit for all of the areas, same as here. And what we see in the white columns for the case with one migration matrix, that's effectively the status quo. So that is for each recruit, each coastwide recruit that the population gets, this is how much yield for that recruit that each area gets. So most of the yield per recruit gets accrued into area 3A in this case. That's the case for the coastwide when you sum the one for all of the areas. So if we were to fish like the survey, as you see here, for all of the areas and for the coastwide case, there's a reduction in the yield per recruit. In this case is when we are taking into account the fact that we need to have the same level of protection at the status quo. So for both cases, fishing like the survey or fishing like the commercial shift results in a reduction on yield per recruit, and also in some changes in the distribution of the proportion, basically the spawning biomass per recruit per area. So I will not spend much time here for time reasons. If we use a different migration matrix, in this case the one different for juveniles and for larger fish, we see the distribution of yield per recruit changes from the previous case, but overall results are the same when you constrain the analysis to have the same level of protection as the status quo on spawning biomass. There's a decrease in the spawning biomass per recruit, and the harvest rates that will have to be applied are very similar to the case of the one area, and again are lower than the current target harvest rate. Last part of the analysis is the one on gradual changes in selectivity and minimum size limit. As I mentioned before, two patterns. Gradual shift A assumes that most of the changes in selectivity will, most of the changes in a gradual change in minimum size limit will affect the selectivity of smaller fish only. And pattern B, which effectively assumes that the shape of the whole curve shifts to the left. And this is very busy, so I'm going to take some time to explain some of these panels and what they mean. This is basically the basic detailed output that you can see in the Blue Book and RARA documents, and these are basically isoplates or curves that have the same properties. So what we see in this axis is harvest rate, and what we see in this axis is minimum size limit from 65 centimeters to 85 centimeters. And the thing to look at here is if you have things that occur in parallel or results that are in parallel, it means that there hasn't been much change from changing the size limit or the harvest rate. And what you need to look at, what is parallel and what is perpendicular or across the lines, if you will, are for these crosses here. This black line there is the status quo condition, that is a size limit of 31.3 and a target harvest rate of 21.5. And the crosses there are those combinations of minimum size limit and target harvest rate that will result in the same protection to a spawning biomass. And that's effectively what you see here. That's the panel of the percentage spawning biomass per recruit relative to virgin. So since we are controlling for that effect, obviously it's going to be parallel to it. So this plot only shows that. There's not going to be an effect of changing the size limit on this variable because we're controlling for that, not changing. In terms of yield per recruit, again, that's the status quo. And as we see, by reducing the by reducing the minimum size limit and therefore reducing the target harvest rate, we see that this line starts to cross those lines of yield per recruit. And as we see, go from something that is above 3.75 to something that is about 3.5. So effectively, we're going across the lines and we are reducing yield per recruit under this assumed selectivity. In the case of average female at age, reducing minimum size limit actually do not cross any lines, but it's going towards that direction. And it's the smaller the minimum size limit is, the larger the average female on the ocean is, but it's relatively small. It's a change of about 4%. Then in terms of the average weight of the catch, as we can see here, the status quo is here. If we start to decrease the minimum size limit, effectively we're crossing the lines again, and that means that as we lower the size limit, we're going to be having or expecting to have a smaller average weight of the fish in the catch. So going from something around 25 pounds at present to as lower than 20 pounds if we were to go down to 65 centimeters. In the case of the change in numbers in the catch, that is how many fish are going to need to be handled comparative to the status quo. It will mean that as we go down, again, we're crossing the lines. So for example, here it will mean this is 0, this is the number of fish we're handling under the current situation. If we lower the size limit, effectively it will mean that we will have to handle, in this case, up to 30% more fish. In terms of discards per recruit, those are going to decrease because we're going to be keeping some of the fish that now we are discarding and dying. But again, even if it's crossing the lines, the effect is very small. So it's around from 0.25 pounds per recruit to about 0.1 or a bit 0.1. So that is about less than 10% of the yield that we get now per recruit. So I explained those panels in the previous thing, so I will not spend that much time with this selectivity shape, but suffice to say that, again, we're actually a little bit crossing a line here, and it's meaning that at an extreme, under these selectivity assumptions, we're going to be, again, losing yield per recruit if we lower the size limit, and suggest that at most, here on this part of the curve, we will gain about 3% of yield per recruit by lowering a tiny bit the size limit. Again, under all of the assumptions we're making about these selectivities, and again, entailing a lower harvest rate, target harvest rate that we currently have. So again, the changes in the average females in the ocean are in the order of less than 10%. The average weight in the catch will decrease. Similarly, the number of the percentage change in the number of fish that need to be handled will go is expected to go up by as much as 60% from where we are now, and again a similar pattern for the discard per recruit. So another thing that we want to highlight here is, well, if it is so hard to predict how selectivity is going to change to in relationship to the minimum size limit, perhaps monitoring our landings can inform us in the future about how that selectivity actually changes into the future, rather than trying to predict it and then potentially failing to meet that prediction. And to do so, I would like to come up landings data we have on the, in this case, the percentage of commercial landings that lie below the current minimum size limit. That is the percentage under 32 inches, and then the fraction by size for each of the areas of that we manage. So again, for example, in this case, for all of the plots, that's the minimum size limit. And what we have here is the percentage that is currently landed. In this case, this is for 2008. That is below that size limit that has been in place for several decades. So as we see, it goes from a high of almost 9% in 2A and about 8% in 2B to as low as less than 1% for areas in Alaska. Overall, coast-wide, 3.23% of the landings are below the current minimum size limit. So the thing is that here, the point that can be made here is like, well, if we actually had observations, precise observations or monitoring of the landings for each area, then we could actually know how a current or future size limit may actually affect the landings and therefore selectivity. However, in the only area that we actually have a full monitoring of the landings, which is in area 2B, is one of the ones that actually has the largest percentage of undersized fish. So if the catch is monitored, but the enforcement of the whole system is actually not providing necessary incentives to actually have this number to be small, then we cannot expect to be able in the future by similar monitoring to know how selectivity may change due to changes in size limit. Finally, into one of the other parts of the rationale for moving to a lower size limit, as I mentioned before, it is based on the large and increasing estimates of total biomass of fish H+, and that being estimated to be different from the declining trends that we see or we estimate on eBio and that we see on the survey weight per unit of effort. And as you're going to be seeing in the next presentations, we have the recent assessment has something that is called a retrospective bias, that is estimates of early biomass, both for total biomass and explorable biomass, that are estimated to be high when they're first looked at. Then it takes us several years later, several assessments later, to actually find out that the level may not have been that high and that the trends could have actually been different than what they were estimated at the beginning. So under the current retrospective or ongoing retrospective bias that we've seen in the stock, at least in 2006, that resulted in overestimation of biomass and the reversal of those increasing trends. This again brings a word into caution about the potential impacts of dropping the size or changing the size limit under those circumstances. A quick summary, those are the approaches that we follow for looking at the potential changes in size limit. The first one, as I said, in terms of female selectivity and maturity at age, what we found was that, actually was one before, what just highlighted here, with the current minimum size limit, areas 2A, 2B, and 3B have a larger capture of immature females than other areas, and further lowering the minimum size limit is expected to increase the catch of immature females up to 4 years before they mature, and this is based both from modeling results of assumed selectivity, but also looking at the realized selectivity, if you will, from historic periods with different or basically smaller minimum size limits. Under those results, lowering the size limit is not expected to be a precautionary approach based on life history theory. This is basically a common sense, but it's also works that show this through simulations, is that it is a precautionary thing to allow females to reproduce at least once before they start to be caught by the fishery. The yield per recruit analysis and biomass per recruit show that using the current harvest rate and lower selectivities for the commercial gear or shifted to the left will result in a reduction of the level of protection to the spawning biomass to about 82% and 47% of what we are expecting to get with the status quo. If we constrain the analysis to actually provide the same level of protection to the spawning biomass, then the target harvest rates will have to be precisely controlled at lower levels than we currently have, but still it will result in about 10% lower yield per recruit that we're getting now from the stock. The migratory yield per recruit and biomass per recruit is very similar results to the single area, and it also showed the level of protection is actually changed, is different for different parts of the coast, and is expected to be lower in area 2 than in area 3, and this is consistent with past widget results that you saw over the years. Finally, the analysis on gradual changes in selectivity and minimum size limit suggests that, or indicates that, reducing the minimum size limit will result in a reduction in yield and spawning biomass per recruit when we are controlling to have the same level of protection. The only increase in yield per recruit that we get is at most 3%. It will require precise control of a lower harvest rate, and at the extreme, if we were to lower the size limit significant to the left, still the females are going to be predominantly in the catch, and that will result females in the population overall to change at most from 44% to 45% for ages 6 and older, and the largest change will be in age 25. That will be going from 12% in the population to 22% in the population. So not much of a change in that variable. As a conclusion from this analysis, it can be said that lowering the minimum size limit is actually not supported by the analysis we have at hand.